All right, our last week of the semester for new information, we're going to be studying some RL circuits. So we're going to put an inductor and a resistor in a circuit and analyze them. So we're going to analyze circuits that have an inductor and resistor and describe how current and voltage exponentially grow or decay based on initial conditions. Inductance, okay? If you have, Faraday's law of inductance relates the amount of voltage and how much current will be induced in a loop based on the change in magnetic flux, okay? So we saw that last week, and then we know based on AC circuits that changing flux induces that change in current, which is known as self-inductance. So now what we're going to do is take that. So a lot of that manipulation is in AC. So transformers have to use AC current in order for that to work, to go back and forth. So an inductor essentially kind of prevents AC from really or going through, because it's actually producing its extra current. Okay, but DC can flow right through it. And in fact, that's what we're going to be looking at today. Once it's on, there's kind of a little bit of a delay in the current, and then it gets kind of ramped up into a steady state. And then that coil acts just like a regular wire through the system. Okay, so if we go back to my very first slide here, you know, I love these little memes. So this is not actually why, but DC current can go through an inductor, but AC current doesn't really. It gets manipulated. Just like in a DC circuit, our DC builds on a capacitor. However, AC doesn't. And it's not actually because of this. This is just a joke that AC goes up and over. But really, it's because it's constantly going back and forth, back and forth. So that buildup is not happening like it is on a DC circuit. Okay. So what's happening here with our voltage in an inductor, okay, so that voltage is happening when our switch is closed and open. We're going to look at those in detail on a on a millisecond scale. Okay, so but this is just for the voltage supplied here. So your inductor current, that's the current going through the inductor. You can see it kind of ramps up. And then you hit that steady state until you open the switch again. We're going to be focusing just this week on when we turn the switches on, okay? And so what happens here is my voltage, as soon as I switch it on, my voltage on my inductor is up, and then it kind of goes back down to zero, and then we hit that steady state where that inductor is just acting like a regular wire, okay? And again, this is the voltage of the power supply. So that's if you were measuring it over the battery. Okay, we are also going to look at the current and voltage for the resistor. Okay, and the first little intro lab that you're going to do is all you're doing is watching those graphs. You're going to make a couple calculations, not based off the graphs though, just based off the values. But in the lab, you'll actually look at the graphs and see what's happening in that circuit. So an inductor resists the change in current until it builds up, okay? So remember, as the current goes through, it's building up, it's storing that energy in that magnetic field. And then once it's kind of built up to its maximum, what happens, you get that constant current in a steady state circuit, just like you just had one resistor in a battery again. Okay, so we have a new time constant here. So we still have that tau. We had a tau for our RC circuit. Now our tau is for an RL circuit, which is L divided by R. Okay, so our inductance divided by resistance. Its unit still is seconds. And just like before, one time constant as it's turning on is going to get us up to about 63% of that overall current. Okay. This is what's causing this delay in turning on and off. So if you've ever turned something off and it kind of looks like it dims a little bit, it's most likely due to having some sort of an inductor within that circuit. Okay, there could be a variety of reasons, but that is one of them. So here we have a couple of graphs. This E is representing E as in the EMF. So we have our inductor, our current for an inductor, and our voltage for our resistance. So our voltage from our resistance is going to kind of build up gradually here, just like our current is going to kind of build up gradually. All right, there's a little bit of that delay when you first turn that circuit on, and it's because of the inductor, and it's resisting it at first, and then it's going to go into a regular steady state. Okay, and I have this again in the next slide, but note this equation. That's the one that the primary one that we're going to be using. We're not going to worry about when we turn it off, but we're just going to look at turning it on this week. But just so you know, for that at any given time, we have our naught or max e to the negative TR over L. That is if it was turning off. Okay. We are not going to necessarily worry about that in our course, but just for those of you who may need that as a future reference. Okay, so same thing here. This is the voltage for our resistor, and then this is our voltage for our inductor. But as I mentioned, we're going to kind of focus on our current for this week. So here is our current for both when we're turning on and turning off. So just like before, where we have one time constant, this would be the current of the circuit here. So we're getting up to 63% for that first time constant, or we're decreasing when we turn it off by that 37%. And this is, again, what's usually happening. Our maximums here this is both for our inductor, so the current and then the voltage, but again, we're just going to focus on the current. Now, you've probably seen this written a few different ways. Just so you know, this E to the negative RT over L is the same as doing E to the negative T over tau, right? Because for an inductor, tau is going to be L over R. So if we're doing T over tau, okay, this tau ends up being, it's L over R, so then it's going to be T over L over R, so that's where the R comes up to the top. All right, so just please make note of that, or if you already have your tau, you don't have to use the R and L again, you can just use tau itself, okay? So this is from Hyperphysics, the link is down here. Again, I love these as little kind of summaries. We're getting these equations the same way as we did before, but we're looking at the Kirchhoff's loop rule. All right, so we have our total voltage, our voltage over the resistance, which is IR, and then our voltage and our inductance. And this is the equation we used in week 14, where L is the change of I over change in time. Okay, and so then when you work it all out, we can determine our current through an inductor, and then this is going to be the voltage. Now remember, the current is the same current through the whole system, so it's not going to be really changing. It's our voltage that's different across the resistor or inductor depending on what's happening. But again, your current is that one flow of charges, so you can use that current through the inductor or through the resistor. Okay, but again, in your max, change colors here. This here is written as V over R. That is your I max. Okay, so the maximum current is when you only have just the resistor and the voltage. So that's just your V over R. That's basic Ohm's law once again. Okay, so if you're not sure what the maximum it is, you can throw that in there. Your expert TA this week has a few questions like that where they use E here instead, but they're asking you for that. They don't have an IMAX option. But just remember, when it's at that steady state, we're going back to Ohm's law again. Okay, so I've got several little practice problems here. This first one is just looking at this equation here, that our tau is going to be L over R. Okay, so if you want a characteristic RL time constant of 0.05 seconds and you have a 500 ohm resistor, what's the value of the self-inductance needed? So we're just setting that up like this. So your L should be about 25 henries. And then a large superconducting magnet has a 50 Henry inductance. If you want a current to be adjusted within 1 second, what's the minimum? Well, if you want your 1 second to equal 50 over what? That's got to be another 50. Okay, and so those are those two answers there. That's just working with the time constant equation for inductance. All right, this next question, we're looking at a circuit. So what is the characteristic time constant for a 7.5 millihenry inductor with a 3 ohm resistor and a 9 volt battery? Okay, so at first, if it's just asking for our time constant, we don't actually need the voltage, but that may be required later. Okay, so you can just do your time constant, which is L over R. You plug in, make sure you change that to regular henries, divided by 3 ohms, and we end up with 0.0025 seconds or 2.5 milliseconds. Okay, so find the current point or 5 milliseconds after the circuit is initially turned on. Okay, so that's why we're going to find the current at a certain time. So we're going to have our I max, 1 minus e to the negative. We already know tau, so I'm going to do t over tau instead of having to use r over L or RT over L. Okay. Now, we're not quite sure what our I max is yet. You can calculate that in a separate equation, or you could just plug in that we know 9 volts over 3 ohms, 1 minus e to the negative t, which is our 0.005 seconds. Always double check those units. And our tau. Okay. So work this all out. Pay attention to obviously your negatives, 1 minus that. When you get everything in there properly, you should end up with 2.59 amps. All right. So these should be kind of familiar from our RC circuits. It's a very similar concept, very similar way of solving. It's just making sure we're using the right form of the equation. As I mentioned earlier, we're not going to worry about when we turn the switch off. We're just going to look at when we're turning it on. So that would be like the charging versus discharging in a capacitor. In this case, your circuit is either ramping up when we turn the switch on, or it's ramping down when we turn it off. Okay. So current in an RL circuit, I took this one from your textbook. If you ever feel like you need extra practice, the odd questions have those answers to them. You can double check your work if you want. But they've got a good couple of questions at the end of chapter 14, and they also have some pretty good examples throughout the reading. Okay. So the current in an RL circuit shown below reaches half of its maximum value in 1.75 milliseconds after the switch is thrown. Determine the time constant of the circuit. Okay, so in this case, you may be thinking, well, how do I know the time constant if the next question is actually asking me for resistance? All right, but we can use the current equation, right? So I'm going to write up here. So we have I at a specific time is equal to our I max, 1 minus e to the negative t over tau. Okay, so we know t. We're looking for tau. We're trying to find e, or no, not trying to find e. We know e. Okay, and then we actually know these two right here as a ratio. All right, so when we do t and we divide that out, max, we know that that's going to be half of its maximum. So that's going to be your 0.5. All right. And then that's going to equal, okay. So this term right here is 0.5 because it says half of its maximum. So when you divide that out, you would get that 50% or 0.5. You can plug in your other numbers and you should end up with a time constant tau of 0.00252. I kept 3 sig figs on that one. Or on the next slide, I have it in milliseconds, so milliseconds. And then you can use that tau in your equation here to solve for your resistance. So we know this is 0.25, L is 0.25, our tau we just determined right here, so we can determine our resistance is going to be L over tau. Wow, sorry, writing is struggling today, which ends up as 99 ohms. Okay, so there it is there. Again, this is written in milliseconds. After 15 weeks, you guys know to be careful with Expert TA on what it's asking you to answer your question in. Okay. Okay, one last one here. This one is similar to one in your Expert TA, and that's why I've used it. It's going to be a little bit repetitive here because we're looking at half its maximum value again. But I wanted to show how to express your answer in terms of time constant, because you were doing that, or how many time constants in one of your questions. Okay, so this is very similar to how we set up the other one. So how long after a switch is thrown does it take the current in the circuit to reach half of its maximum? So we have E at a certain time is our, sorry, not E, I max 1 minus e to the negative t over tau. Okay, so when I divide, once again, I t over I max, that's going to be my 0.5, okay, because that's 50%. All right, whoops, wrong one. So we're going to have our 0.5 is equal to 1 minus e to the negative t over tau. Okay, so we're going to subtract that to get 0.5 is equal to negative e is to the negative t, over tau. So our negatives will cancel out, and now we're not taking the natural log of a negative number. Okay, and then we are going to do the natural log of 0.5, and then so that's going to end up being okay, now it says in terms of tau, so my time, if I multiply both sides by tau, is going to be 0.69 tau, okay? So there you go.